Thank you for joining us this afternoon for this ATA educational webinar series, Modeling Thermal Management of Electronic Systems in Siemens Simcenter FLOEFD. I am your host, Scott Tipo from ATA Engineering, and with us today is our guest speaker, Richard Ozaki from Siemens Digital Industries Software. Before we begin with the webinar proper, I would just like to give an introduction to our sponsor, ATA Engineering. ATA Engineering is an employee-owned small business with a full-time staff of almost 200, may even be over 200 now, most of us being degreed engineers. We are subject matter experts recognized by a variety of professional societies, and we have a number of professional engineers, licensed, registered professional engineers on staff, and an average of 15 years experience in our particular fields. These particular fields tend to be aerospace and defense, robotics and controls, themed entertainment, think animatronic figures, attractions, roller coasters and such, industrial and mining equipment, consumer products, and others. Essentially, ATA Engineering's core business is to help our customers address their most challenging engineering problems. We provide these services from our offices nationwide. Our principal headquarters office is in San Diego, California, but we have branch offices in Los Angeles, the Bay Area, Denver, Albuquerque, Huntsville, Alabama, where I am myself located, Washington, D.C., and now our brand new office in Boston. From these offices, we provide services for design, analysis, and test. ATA Engineering is perhaps the largest independent provider of ground vibration tests for aircraft, satellite systems, launch vehicles, rocket engines, and such in the country. We are also a platinum level solution partner for Siemens Digital Industries Software. As a solution partner for Siemens, we provide training, licensing, hotline support, implementation services, software integration, and more. We support products like NX, Nastran, VMAP, Star CCM+, Simcenter 1D, Simcenter 3D, which we're talking about today in the form of FLOEFD, and Teamcenter. You might be interested to know that ATA is actually the preferred Siemens training provider for Nastran, and all of the training materials used worldwide by Siemens are created by ATA Engineering and maintained by ATA Engineering under contract to Siemens. If you'd like access to lots of resources on Siemens software, you can visit us at our website here, where you can access white papers, presentations, macros, other resources, past webinars like this one, and much more. We hope that you take the time to come and join us. Our presenter today is Richard Ozaki from Siemens Digital Industries Software. He is part of the Siemens Simcenter team specializing in CFD analysis for fluid flow and heat transfer. He has a background in mechanical engineering and has been at this for over 15 years. And he also came to Siemens with the acquisition of Mentor Graphics some years ago, Mentor Graphics being the company whereby Siemens acquired the FLOEFD tool that we will be looking at today. Take it away, Richard.
Thank you so much, Scott. So I'm going to take the screen from you and share. And what I'm going to do is just quickly do a few slides on FLOEFD, if that's okay, and then I'm going to jump into a live demonstration of the software. So the first question I often get about FLOEFD is, hey, what's with the name? What's FLOEFD stand for? So originally the tool was just called EFD, and that stood for Engineering Fluid Dynamics. So really this tool is something that, it's a CFD tool, but it's designed and positioned towards engineers or designers. And let's dig into that a little bit more. So FlowEFD is part of the Simcenter family of products, and it's available within the Simcenter 3D product. So you'll notice we have the Simcenter 3D wheel here, and we have a thermal section here where FlowEFD fits in. Now, it is a general purpose 3D CFD tool, as I mentioned, designed for non-CFD specialists. Okay, it's very accurate. We have a ton of validation documentation that comes with the software, and we're really trying to democratize CFD and put it in designers' hands rather than analysts' hands. And because of that, it is a CAD embedded solution. So the tools that it's embedded in from the Siemens Digital Industry software side would be NX, Solid Edge, and Simcenter 3D, which we'll be looking at today. We also support some competitive tools like SolidWorks, Creo, and CATIA. So it really integrates into the workflow and can perform a wide variety of CFD simulation tasks, as you can see on the screen. So as simple as mixing fluids, we can also look at external flows like aerodynamics, rotating equipment such as pumps, fans, and impellers, heat exchangers, combustion and fire modeling. We can also do some free surface modeling as well. So as you can see, a wide variety of applications, but a specific area where FlowEFD has really carved out a niche is in the electronics cooling space. Whenever you need to do, board level analysis, chip level analysis, fans, heat pipes, guiding airflow. This is an area where we've had a lot of success and we've got a lot of functionality in FlowEFD, and that's what I'm going to be talking about today. So let's just have a quick look at what FlowEFD looks like in action. Here's a simple valve that we can have a flow analysis on and look at the flow from inlet to the outlet. Now, the nice thing about being CAD embedded is that you can make some pretty big changes to the geometry, such as changing the angle outlet using synchronous modeling here, and then just running the analysis again, right? To actually do that in a traditional tool, you'd have to go back to the CAD tool or perhaps the CAD department, have that change done, and then rerun everything and get a new step file. Okay, another example of that is looking at parametric variations. Here's an LED heatsink analysis, right? What if we had control of all the CAD parameters so we could actually drive sketch dimensions, pattern dimensions, really look for the most optimum combination of parameters, maybe some combination you hadn't even guessed on, and let the software find the best one, right? The lowest temperature plus the lowest mass. We can really optimize on parameters which you can't really do if you're just working with, say, a step file or a Parasolid file. Okay, and that's really the benefit of being CAD embedded. And finally, I wanted to mention that FlowEFD, it is part of the Simcenter 3D world, and it's accessible via value-based licensing or tokens. Okay, so you buy a token pack from ATA and you have access to everything in the wheel. So let's say you start by buying tokens to access the structural analysis portion of Simcenter 3D, which is its core competency. That's great, but then maybe 6 months down the line you have a request for doing additive manufacturing or motion or acoustic simulation or thermal, which we're going to be talking about today. So you have access to everything in this wheel if you purchase tokens. It really future-proofs your investment and allows you to leverage all the capabilities of Simcenter 3D, which, by the way, are getting added to with every major release. So watch this space. Okay, with that, I'm going to jump into a demonstration of FlowEFD and kind of show you what the software looks like, a little bit of a look and feel of the tool. So as you can see on my screen, I have an electronics box, right? So this might be like a set-top box or a router or some other, consumer electronics piece of equipment that you might have in your house, okay? You can see there's a folded sheet metal case and cover. There's some electronics in there, and if I just hide these parts, we can see we have a fan driving airflow with an arrow showing the direction. We have a extruded aluminum heatsink here. We also have a representation of the board with some blocks to represent the chips that are on this set-top box. Okay, and we'd really like to understand what the maximum temperature of the electronics are going to be. Is my heatsink big enough? Is it too small? Do I need to adjust the fin parameters? Is my fan in the right location? Are my holes in the side of my casing, are those sufficient? Are they in the right spot? Right, you might just take a guess at some of these parameters based on, tribal knowledge or past experience. But if you'd really like to understand if your combination of design parameters are fit for purpose, you need to do analysis. And that's really where FlowEFD comes in. So this is Simcenter 3D. We're currently in the modeling mode. So let's go into FlowEFD mode. So Simcenter 3D has a variety of different modes based on what you're trying to perform. But FlowEFD simulation is one of the modes. And if I switch into that, you'll see that at the top here, this changes to FlowEFD simulation. Now, Simcenter 3D looks and feels very much like NX. Right? And that's because it is a subset of NX. It's a stripped down version of NX, which allows you to do CAD modeling and CAD manipulation and importing of CAD data from competitive tools. And then it has all of the analysis capabilities bolted on top. So if you're an existing NX customer, this is a really great way to take advantage of the geometry that you've built and perform analysis embedded within that NX environment. So moving on to FlowEFD, you see that we have this flow analysis tab up here. Is one of the ribbon toolbar items, and it looks daunting. There's a ton of buttons here, and we also have the FlowEFD tree combined with all the parts tree that we saw a second ago, where you can turn bits and parts on and off. You have all the constraints for your CAD assembly. If I was within a part, I would see all the part history here as well. But FlowEFD is also an extra icon here. And what I'm going to do is I'm just going to step through the wizard real quick and show you some of the features within this tool. So you can choose a unit system. Okay, I'm going to be using an SI focused unit system, but I can also choose a US unit system as well to go to Imperial. Now, here, this is important. There's a few different analysis types that we can switch on and off based on what we're looking to perform, right? Fluid flow and conduction, that's typically all we need to do. We also have a structural solver, okay? If you need to do an FSI simulation, then we have a structural solver, which can solve for static, frequency, buckling, and new is non-linear capabilities now in FlowEFD. So we're actually taking the Nastran solver and porting it inside of FlowEFD for doing FSI. But I don't need that for now. We also have EM. Okay, electromagnetic simulation, low frequency, so things like magnets, solenoids. We can have a look at electromagnetic fields and how that might affect things like traces on PCBs or voltage or current that's induced in conductors due to magnetic fields. We can absolutely do that. Radiation, time dependent is your transients. Gravity, I'm actually going to turn that on. Okay, so if there is natural convection, then we need to set a gravitational direction denoted by this arrow. We also have rotation for, again, pumps, fans, compressors, turbines. Free surface for when you have a gas and liquid interface, such as the surface of the sea. We can have a look at the sloshing effects and the droplet formation. So as you can see, there is a lot of capability in here. And quite a lot of overlap with our flagship CFD product, Star CCM Plus as well. Okay, moving on. I'm going to choose air as my working fluid. No, it's not under liquids, it's under gases. And as you can see, we have a wide variety of fluids predefined in the database, even going as far as steam, right? So we can have a look at steam to water condensation. We can also look at phase change. So we do have phase change refrigerants in our library as well. And with air, we can actually look at humidity effects also. Default solid. So I'm just going to choose, let's just choose steel. Let's just come down here to mild steel. Okay, so that's basically setting the standard material. I'm not going to worry about roughness. And here's my ambient conditions. Okay, so let's say this set-top box is operating in the Arizona summer, let's say it's going to be 45 degrees C, okay, or about 120 Fahrenheit. Okay, worst case scenario. So I'm just going to click finish. And what we're going to get around the geometry is a computational domain, right? So you can see we're getting a volume around the electronics enclosure where our air is going to be modeled, where our heat transfer is going to be modeled. And it's a little bit big right now, so I'm just going to go normal to the screen. And I can just grab my edges of my domain and just pull those in a little bit because I just want to reduce the amount of reduce the analysis scope. Okay, and again in this direction as well. Simple as that. And I just click, and now we have our new computational domain specified around my electronics enclosure. No need to create a separate part to represent the air volume around my electronics. Just resize the domain. Now, as I mentioned, FLOEFD has a lot of additional capabilities around electronics cooling, right? So we have things like two resistor and network assembly models. We have thermal joints, thermal resistances, thermoelectric coolers, heat pipes, printed circuit boards, LEDs. We have electrical conditions, so voltage and current sources that we can define on conductors. We have electrical elements and IGBTs for high power electronics. We also have things like smart PCBs. So these used to be modular, but now with the tokens in Simcenter 3D, you'll get everything that you can see on my screen as part of the token system in Simcenter 3D. Again, a great way to future-proof this particular tool. One thing I did want to touch on is the EDA import capability of FLOEFD. So at the moment, I do have an assembly representing my PCB, but if you want a little bit more detail, then we can actually pull in a much more detailed representation of the PCB using the ODB++ ECAD file format. Okay, ODB++ is a bit like the step file of the PCB world, right? It includes everything inside the board for manufacturing purposes, for data transfer purposes. But what you get with this is really all the layer information, right? If you use IDF or an outmoded representation of the board, you don't get all the copper definition within the PCB, right? As I step through the layers, let me just zoom into this BGA here, right? So this BGA is soldered onto the board. It's reflow soldered, and you can see there's these pads where the balls sit down. Then they fan out to these vias. Now these vias, if I zoom in a little bit more, they're copper-plated holes, and they connect with the layers within the board for electrical connections, right, for voltage. And then the logic is performed on the chip, and then it will control something else on the board. So although these are primarily here for electrical connections, they're also very important thermal paths as well, right? You can control things like the diameter of these vias, the plating thickness of these vias. Some vias are also filled with solder to increase the thermal conductivity under high power components. So, if you just use a block representation of that, of the chips and of the board, you're missing a lot of the crucial heat transfer paths that the ECAD team have so lovingly created, right? They created these thermal paths on purpose. And if we're not modeling that, we're doing them a disservice. So the EDA bridge allows us to pull that data through and use a smart PCB representation of the board. Okay, I'm not going to actually click transfer because it takes 2 or 3 minutes, but I do have that already built over here. And what I'd like to do is just quickly show you what that looks like. So where is my, yep, it's this one. Let me just go open in window. Okay, so I do have a sub-project defined on here, and I do have this smart PCB. And as you can see, look, if we look at this legend, it ranges, I'm plotting by thermal conductivity, watts per meter Kelvin, between 0.3 and about 400, right? So 0.3 is your dielectric FR4, and then 400 is the copper. And this is really what the smart PCB is doing. It's pulling through that data. Now, if I zoom right in, it does get pixelated, right? All analysis, has to discretize at some point. So there is some pixelation there, but at a high level, you can see the absolute amount of detail that's created in this smart PCB in all the layers and all the heat transfer paths through the board. Okay, and rather than modeling the copper explicitly, what FLOEFD is doing is it's creating a conductivity matrix based on pixels within the board, right? As you saw, as I zoomed in, each one of these pixels has a conductivity to it, and it's linked to the neighboring node using a thermal resistance, right? So it's basically one big matrix of thermal resistances. Now, this is a very, very detailed board. It is computationally expensive to model a board at this sort of fidelity. So rather than using the fine level of modeling, I can move to a averaging method, right? And what that does is it creates a pixelated representation of the actual geometry. Okay, so it's just calculating this new pixelation now, but as you can see, we don't have as fine or as granular density of pixels as we saw a moment ago. So although it's not the absolute geometry for a thermal analysis and the conduction paths through the board, this is actually good enough, right? And you as the user can actually control the level of fidelity using this. You can see here, if I hover over it, number of tiles per layer's longest side, right? So if I make that a little bit higher, for example, and just click off the box, then it's going to be calculating the new pixel density, and it will update and show me what the new conduction paths look like based on the pixel density. Okay, so I'm not going to do this. I'm actually going to go back to my fine level modeling for now. It looks better and for demo purposes, right? But just to show you that we have different levels of fidelity for modeling PCBs. Okay, let's come back to the top level assembly. Okay, and go back into FLOEFD mode and go to my flow analysis. Other things we can do. So the PCB is taken care of, right? We have the board. I skipped over assigning powers onto the chips, but I'll show you that in just a moment. But other parameters, let's say we wanted to add a material to the heatsink. I can just come to insert solid material. Okay, at the moment, remember everything's steel. I can click on my heatsink on the screen, predefined, alloys, aluminum 6061. Tick OK, simple as that. Let's hide this guy. We also have a TIM under here, right? So if we do want to create a custom material, again, we can absolutely do that. Click on solid material, click the TIM. I can click the create edit button. And let's go to materials, solids, user defined. And let's just call this TIM, thermal interface material. I do need to give a density and a specific heat. You can grab from the datasheet, but the most important thing here is the thermal conductivity. Let's say this is going to be 2 watts per meter Kelvin for this thermal pad. I can save it. I can now select it. And now we have the thermal interface material assigned on that part. Okay, if you wanted to, we could also assign a thermal resistance. Rather than modeling the TIM as a solid part, we could have a thermal resistance between the two parts. So I could give a material and then define just the thermal resistance, right? And then that will define my thermal resistance between the TIM and the heatsink. Other things we can do, let's look at this fan. So if I come over to my, where are you? There it is. Here's my fan. I can build into my fan. This is going to be an internal fan. So I need to select the face where the fluid exits the fan. So that's going to be this side over here. And you'll notice that I've removed the blades of the fan and I've got just a planar surface that I can click on, right? That's just a little bit of geometry preparation you need to do because spinning the blades, yes, it's possible. it's also very computationally expensive, right? So if we can take some shortcuts somewhere, we will. So I've just kind of remove the fan, remove the blades, and just put in a planar surface here where the flow will be sucked in from, and then ultimately blown out the other side. And then we need to link those two sides of the fan together with a fan curve, which we can just pick from some manufacturer data sheets that we have built into the software. And if you would like to see what that looks like, then we have, you can see the flow rate versus delta P of this particular fan, and based on the resistance, it will operate somewhere on this curve and blow at a certain flow rate. Okay, and now you can see we have the fan blowing through the model like this. Oops, excuse me, blowing through the model like this. All right, let's just bring back my heatsink and my case and my cover. Okay, so we're almost there. Let's say we've done all the pre-processing on this. We now need to define the computational mesh on my model. Okay, so moving from left to right in my toolbar, I can come over to my global mesh. And we have two options, right? Automatic or manual. So if I just click my basic mesh, it looks kind of coarse. Now, FLOEFD does use a Cartesian meshing schema, right? We don't have TET, hex, polyhedral cells. It's purely Cartesian in nature. Coming back to the way we democratize CFD for CAD designers, you don't want to be a meshing expert. You don't want to worry about boundary layer meshing, right? You just want to get an accurate result quickly without sending it to the CFD team. So with that in mind, we have just a Cartesian meshing schema, and it's what's called an immersed boundary mesh. Okay, and I'll talk about that in just a second when we look at the results. But we can manually define things like the mesh size, the overall mesh size. If I want to make this finer in the X, Y, and Z direction, I can absolutely do that, right? So I can set my base mesh size. That's maybe a little bit too fine because we're going to be breaking the mesh down further from here. And then we can do things like control the channels. There's some advanced refinement here, which is all part of the advanced training course. But we can also add in what's called a local mesh. So let's say you want more mesh on a specific part, let's say the heatsink, then we can add additional mesh by moving these sliders on specific parts inside the model, and that will ensure that critical parts have sufficient mesh resolution. Okay, what I'd like to do is just kind of jump over to model I've already solved and show you what the final mesh, the final generated mesh looks like. Okay, in fact, let me just take a slice through the model. In this way, let's just preview that, and I'm just going to pull that through my heatsink like this. Okay, and let's hide all the geometry. Okay, so this is what the final mesh in FLOEFD looks like. So we've set the base mesh size, which is 10 millimeters, right? So 1 centimeter. So these dark blue cells are 1 centimeter or 10 millimeter grid cells. Okay, now if I zoom in to this corner here, the way we split cells and add refinement is what's called octree meshing, right? We take this cube, we split it into 8 in 3D or 4 in 2D. So now these cells are now 5 by 5. We split into 8 again. These are now 2.5 by 2.5, right? And so on and so on. And you can see what this was originally a nice smooth filleted curve we designed in NX, which has turned into a series of facets based on where the geometry crosses the boundary of the mesh, as you can see here, right? Series of flats. So if you need better resolution here, it's just a case of forcing the software to split the cells further, which you have full control on, by the way. All right, so you can see around my heatsink, I've got much finer grid cells, 3 to 4 grid cells between the fins. Another interesting thing is how we can have, fluid, solid, and fluid regions within a single cell, right? You're not restricted to just solid and fluid cells. You can actually have multiple control volumes within a single grid cell. And this is part of the secret sauce in FLOEFD. It's called the immersed boundary method, where we apply a wall function, the boundary layer wall function on this planar surface between the fluid and the solid. I don't want to get into that too much, but I just wanted to highlight that this is a very different approach to CFD than most other tools take. And really the benefit is you don't have to be that meshing expert. You don't have to worry about boundary layer meshing. The software takes care of it for you, so you can get on with the business of actually designing your products. Okay, just a quick word on solving before we move on to results. You do have to run the mesher. It is a finite volume mesher. It is multi-core by default. Okay, my laptop's only got 12 cores. I can select 12 cores. If you have a Threadripper machine with 128 cores, you can use 128 cores. We don't limit you by solver packs or anything like that. If you have FlowEFD, you have full core solving capabilities. You also have the ability to send jobs to a computer on the network. You're not limited to just, a node-locked solve. We absolutely support floating solves, standalone solves, so it frees up your local machine for day-to-day work. And that's all with the standard tokens. That's all completely accessible. So this particular model took approximately 1 hour to solve, something along those lines. And then we can start to have a look at some of the results, right? So I'm just taking a 2D slice through the model here, but I'm just looking at temperature. And as I move this slice through the model, I can probe the temperatures. So my ambient's 25, not 45, as I said, but we can move my mouse around. I can see what sort of temperatures the airflow is getting to, right? The air temperatures within the box. If I don't want just temperature, I can switch over to velocity. And so I can see, look, the outlet on my jet, the outlet of my fan, I can see some jets being formed at about 2 meters per second. I can see, let me just pull this down, let me just pull this up a little bit. I can see some jets being formed between the vent holes, as you can see here, right? So I can kind of interrogate the model using these cross sections, looking at a variety of different parameters, right? Velocity and temperature is probably the most interesting in this case, but we could also look at, let's see if we can look at pressure real quick, right? So there is a very slight pressure difference from the inside to the outside of the box because this fan is pulling a vacuum, right? And there's a resistance as the airflow crosses those vent holes, right? One thing you do need to be a little bit careful on is if you do have a lower pressure inside your electronics box, that's going to be, sucking in a ton of dust, right? This could get very dusty without filtering. So we might want to flip that fan around and actually blow air into this model and pressurize it, right? So again, things we can look at the analysis stage before we've committed to tooling. Okay, let me just jump back to temperature. Okay, so you can see we can take these cut plots. It's not too exciting, moving them up and down through the model. We can also visualize on the screen the actual PCB temperatures, the heatsink temperatures, the hotspot temperatures. If I just kind of zoom in underneath here, you can see, there's this hotspot under my CPU. The rear side of my board is getting up to about 80 degrees C. Other areas are even hotter, 81, right? So there's actually some RAM modules that are hotter than the actual CPU because they don't have any thermal design on these parts. So we can have a look at temperatures, both on the PCB and on, let's say we wanted to have a look on the case as well, right? So if this is a set-top unit, we don't want kids touching this unit and burning their fingers. So 33 degrees, that's more than acceptable, 34. Anything below 40 is about, acceptable for consumer goods. But yeah, we just want to make sure that our case temperatures are low enough. So let's just hide that. And then we can also have a look at what the flow looks like through the model as well. All right, so you can see if I just animate this real quick. You can see flow being pulled in from the left-hand side, from the right-hand side. A lot of the flow actually bypasses the heatsink. It doesn't actually go through the heatsink. Air is always going to take the path of least resistance. So it's recirculating over here. This is potentially where dust could fall out of the flow due to the low velocities that it's encountering and the swirling flow. The air is currently colored by velocity, but let me just change that to fluid temperature, for example. Oh, no, I need to change the range here. Right, so you can see where the hot air in the box that's struggling to get pulled out by the fan, it's kind of recirculating and creating that hot spot on the case, right? So we saw a bit of a hot spot over here. That's because hot air isn't able to leave the case. It's just transferring its heat to the actual casing. So we can kind of, find root causes of some of the problems associated with the electronics and, hot spots, dead zones within the airflow, things like that. All right, so we can generate nice, pretty pictures. We can also extract engineering information from this analysis as well by having a look at the actual steady state temperatures of my critical components, right? So here's my CPU temperature, which is my U1 component. 79.8, temperature of my U24, which is this component here, 64.8. My maximum RAM temperature, 82.57. My flow rate through the fan in CFM, 2.38. So we can get quantitative results from the CFD analysis, including the convergence history. Ooh, doesn't look good. I should have let this run a little bit longer. I was going to say everything should be nice and plateaued. I think I was playing around with the model yesterday before this, but ignore this end bit. But yeah, everything is nice and plateaued, and that's what we're looking for in an analysis. All right, so we've got to this stage now. Most tools can show these pretty pictures, get the temperatures, look at the flow. So what? The real benefit of being CAD embedded is being able to make changes to the model quickly and then understand the delta between projects, right? So because this is Simcenter 3D, which is a NX embedded tool and has a lot of the NX CAD functionality, we can make changes. Like, for example, what happens if we move the fan? That's just a constraint change, right? So I think I'd constrain this fan from this edge over here. What if we make it 4 inches rather than 2 inches? So we just move that fan over a little bit, and then we can load in the results. That's annoying. I thought I solved this. We can load in the results, look at the temperature differences, and compare. We can also drive optimization, right? So we have something called a parametric study, which allows me to select input variables, right? So it can actually look at NX constraints, dimensions, sketches, and use those to drive variance. Yeah, let me just select a not this parameter. All right, so let's go to the case. I believe it's P15, right? So this is a dimension, and then I can drive a slightly different dimension. Let's say 5 mm, or let's say 15 mm, right? And then the software will create a series of scenarios where we actually vary that CAD dimension. It will run them all sequentially. If you have multiple solvers, then like I do, then you can run more solvers than one at the same time. So being able to do these CAD variants is a really big benefit to being, CAD embedded and keeping that CAD workflow aligned with your simulation workflow. And that's really what we're trying to do here with this particular product is, not go to an external tool, not have to be an expert in that external tool, just run it straight in your CAD and, you'll be able to get decent results very quickly. So with that, I know I covered a lot of capabilities very quickly, but Scott, do we have any Q&As around this particular product?
Yes, we do. Let me just take over the screen here. And we'll launch into the Q&A. We have a number of questions, which we'll go through one at a time. But if you have any others that come up in the process of us answering these, please put them into the chat, or alternatively, I can make it possible for you to ask your question aloud. So just let us know in the chat if you would like to do that. The first question is, I am not a user of Star CCM Plus or FLOEFD, but I do use NX and Simcenter 3D. Is FLOEFD a lot easier to learn than Star?
Yeah, I'll take that one. So I would say the simple answer is yes. You know, if you're familiar with the NX or Simcenter 3D environment, this is just an extension of that, right? You don't have to learn, you know, manipulating the CAD and where all the buttons are. It's just another ribbon toolbar within Simcenter 3D. So it's a lot easier to use. In my opinion, it's a lot quicker to get started with things like meshing and solving and post-processing, again, because you're familiar with that CAD environment. So yes, it's easier to use and
So
get
there's
started
a
with.
follow-up question. If I learned how to use it for electronics cooling, like we saw today, how difficult is it to learn all of those other things, turbo machinery, heat exchangers, whatnot?
So the software does come with some tutorials that are baked in with all the models, so you can get started with those. We also have on-demand training for this product available from Siemens, where there's further tutorials and web-based learning. You will also have access to training courses, support, post-sales support. So really, we're here to make sure you're using the tool as successfully as possible.
This one should be pretty easy. We already have some Simcenter 3D tokens. How many tokens are required to run FLOEFD if you already have some?
Yep. So the base pre and post with all the modules is 77 tokens. And then I believe the solver, is 55. Scott, you might have more recent information than me, but you need over 100 to access everything in FlowEFD.
So between 100 and 200.
Correct.
I do have a customer that was doing a trial, and he already had tokens. He was doing a trial of FlowEFD, and he made the mistake of clicking "I want everything" in the tick boxes, and it was taking over 200 tokens. But it's a very rare simulation where you really need to tick all those boxes, so it didn't use a huge amount of tokens. And some of our customers do have 600 tokens, 2,500 tokens, more than enough to run FlowEFD. Here's another question. Would the modeling process for thermal be the same if there was no air? For example, in a satellite application?
Sure. So when I went through the wizard in the analysis type option, I turned on fluid flow, conduction. There was also structural, EMAG. There was a bunch of options there. So I would turn off fluid flow, and I can just do a conduction and radiation simulation. Right. And we even have a specific module for orbital mechanics as well. So if you do want to look at solar radiation impacting orbiting bodies, then yes, we have that capability.
Another question is, does FlowEFD have any automatic optimization as opposed to design sweeps, something like HEEDs or a subset of HEEDs?
So there is a DOE option built into FlowEFD. It is a bit of a brute force approach where it will kind of, create every permutation and combination of parameters. We do also have a HEEDS module for FlowEFD. Now, that particular module is not part of the token pool. I think they don't want to give away the keys to the kingdom there. So that's something you would need to purchase as a line item separately. But yes, we have a HEEDS module.
But one of those could support multiple users if they weren't looking to do optimization at the same time, right?
Correct.
Okay. Another question is, where did it go? What limitations of FlowEFD, if any, would push you to use star CCM plus instead?
Yeah. So I'm glad that came up. So, I get when do you need to step up to the big boy CFD with star? I would say anything with multi-phase, okay? Anything with advanced free surfacing, anything with arbitrary motion. Okay, let's say a boat hull bobbing up and down on the surface of the sea, where you've got that coupled FSI with motion. Anything with long transients, um, I would say very large models. Let's say you're doing an entire vehicle, right? And meshing the entire car or plane, and you want all the nuts and bolts, and you need to solve with an HPC. That's when you would need to move to star. FlowEFD does not have an HPC capability yet. It's really just designed to be a desktop solution for now.
When run on a desktop, Richard, what is the point of diminishing returns when it comes to adding additional cores? I have a customer that bought a single box with 192 cores in it for running Star. Would you reach a point with FlowEFD where more than 20 or 40 or whatever doesn't do you much good?
Yeah, so around 64. 64 to 128, any more than that, and yeah, it's the jump to more cores isn't really worth it.
Gotcha. Okay, we do have some more questions coming in the chat. Uh, from David, are the simulation runtimes with FlowEFD similar to what we would get if using Star, assuming using the same computer and number of cores?
Yeah, I mean, if the mesh count is the same and the physics are the same between the products, I would say you would get similar runtimes.
Well, to
Okay,
be
but
fair, he didn't say the mesh was the same, just that the computer was the same. So
okay.
I don't know that your mesh would necessarily be the same.
That's a tricky one to answer. Because the meshing schema is so different, because the wall treatment is so different.
Well, one of the
Yeah.
things that FlowEFD is particularly good at doing is conjugate heat transfer problems. And the reason for that is that it meshes the solid material and the fluid simultaneously. Whereas in STAR, there is going to be a barrier between the fluid and the solid. You do mesh, you can do conjugate heat transfer problems in STAR, and you do mesh the solid when you do so, but it isn't the same process. So I think you may end up possibly being able to get initial answers faster in FlowEFD, but if you really need to do very fine work and very complicated physics, you might need to step up to STAR. Also from David, do you have much control over the Y plus treatment meshing strategy?
Yeah. So the short answer to that is no. So we don't have to worry about Y plus values for near wall meshing. Again, we use wall functions to it's a customized wall function that we use. It's called the Van Driest profile that's been customized for this particular application. But yeah, there's no way to look at Y plus or worry about it. You can absolutely add more mesh in the boundary layer region. And there's a couple of different ways that we treat that region, but it's not something you can visualize or have any control over.
Very good. And from Ray, how does the CAD embeddedness in SolidWorks compare to what we saw in NX today?
Sure. So we actually have a OEM version of FlowEFD that's we provide. So if you want the SolidWorks version, we can absolutely sell that to you. It comes bundled with SolidWorks.
And is it functionally essentially identical to what we saw?
Exactly. Yes,
Okay.
exactly the same.
Now, one really key difference, though, Ray, to keep in mind is that um, that would be a separate product that you would purchase as opposed to adding tokens to an existing Simcenter 3D installation. Or if you already have Simcenter 3D with tokens, you're effectively getting FlowEFD for free. So that's one significant difference. I think that's the end of our questions. So I would like to thank our speaker, Richard Ozaki from Siemens Digital Industries Software. And thank you, everybody, for joining us this afternoon. If you need any further information on FlowEFD, Simcenter 3D, or any of the other Siemens products that ATA Engineering provides, feel free to contact me with the information shown on the screen. And so thank you for joining us today for this webinar on Simcenter 3D and FlowEFD for electronics cooling. Come back and join us again for our webinar series, which we do several times a quarter on all of the different products that we support, including Simcenter 3D, Star CCM+, AIM-Sim, NX, VMAT, and the Simcenter 3D test and measurement products. Thank you for joining us.